Thank you, Parvati. Good afternoon, friends. Today I'm here to talk about this memory allocation.
Sir, a mouth
As you
piece
know,
on the പിടിക്കാമോ?
hello.
Okay, sir, it's audible.
Hello.
Okay.
Clear.
അതെ clear ആണ് sir.
Yeah. Good afternoon, friends. Today I'm here to talk about non-contiguous memory allocation. As you know, that there are mainly four major storage elements in a computer system. The fastest is the CPU register, and then we have the cache memory, which exploits the locality of reference. Then we have RAM, that is the primary memory, whose speed is compatible with the speed of the CPU. Then we have a secondary storage, which is magnetic storage, and it's abundantly available in the system. As we know, usually a computer program resides permanently in the secondary storage. When the program need to be executed, it should be loaded into primary memory from the secondary memory. And the subject under memory allocation is how to, or what are the different ways in which we can allocate the primary memory to these incoming programs, or how the room is allocated for a primary memory for incoming programs in primary memory. There are two strategies mainly. One is contiguous allocation and the other is non-contiguous allocation. The sequence of instructions in the program is basically a sequence of instructions, and the sequence of instructions and data, when it is loaded into the consecutive locations of the memory, or it is continuously in the program, it is called contiguous allocation. When the program is divided into fragments and kept at random locations or random blocks in memory, then we call it as non-contiguous allocation. The slide, see the figure A represents contiguous allocation. You can see there a process, and the process is next to that. We can see the memory. The process is allocated space contiguously in memory, where it is a contiguous memory allocation, and in the right side you can see process is divided into 3 blocks, and the blocks are first 2 blocks are allocated consecutive locations and consecutive locations, and the third one is allocated a random location at a different place in memory. So this is the difference between contiguous and non-contiguous allocation. Now let us see why do we need to go for non-contiguous allocation. As you know, after routing, the operating system is loaded into the memory, or operating system is available in the memory. Then the ready programs, or the programs which you wanted to execute, will be entered into the memory RAM one after the other, and after some time some of the programs will get completed, and some of the programs will get completed and they are terminated. So when the programs are terminated, the space allocated for that particular process will become free, and the memory will become some used space, then some unused space, those of that terminated process, then again some used space, unused space, like that. Means the memory will contain so many unused holes or storage spaces. So if we want to go for contiguous allocation, these holes should be brought into one place and joined to make a big hole. So this has to be done. If we want to go for contiguous allocation, these hole has to be combined and made a big hole. But this is very time consuming and tedious process. So what we do is, instead of allocating the space in a contiguous way, we divide the program into different blocks and or the fragments, and these fragments are stored into the holes scattered over the RAM. So this is what is non-contiguous allocation. And the way in which we divide the process decides the different types of non-contiguous memory allocation technique. When we divide the process into equal size, the fragments are of equal size, then it is called paging. If we divide the programs not in terms of bytes, rather when we go for a logical type of division, like main program, function, stack, a program will contain the main program and different functions, and it will contain macros, then as stacks. So when we divide it in the logical way, we call it as segmentation. This, when the program is divided into blocks, it is blocks of fixed size, it is called a paging, non-contiguous memory allocation. When it is divided into logical size units, it is called non-contiguous memory allocation of a segmentation. Then let us discuss the concept of paging in detail. The main memory in paging, the main memory is divided into fixed size blocks, as I told you. It is the main memory is the place where these instructions and data are physically stored. Hence, the main memory location are called physical address locations. And hence, the main memory can be treated as the address space of main memory can be treated as a physical address space, rather than telling that main memory is divided into fixed size blocks called frames. What we can tell is physical address space is divided into fixed size blocks called frames. Then we come to the program. Program address space is also divided into blocks of same size that are frames called pages. You know, the program is basically a relocatable code. It's a load module, the relocatable code. Are taken as with it's based on the relative position of the instructions from the first instruction. So CPU generates address consecutively. To access an instruction from the program, CPU generates consecutive addresses. CPU doesn't know that we kept these instructions at or the program is divided and kept at different locations. CPU generates the consecutive addresses, and these addresses are called logical addresses. And the memory, hence the program is treated as a logical memory, and this logical memory is rather than telling that the program's address space is divided into pages, we tell that logical memory is divided into pages. And you can see the diagram, the figure. If you look into, see that main memory is this main memory, and the main memory is divided into 8 frames, and logical memory, that is program, is divided into 4 pages. The size of the page is equal to the frame. And when we want to look up for a particular page, or when we want to search for a particular page, or to see in which frame the particular page is stored, it is assisted by the page table. You can see a data structure, a table between the logical memory and the physical memory, that is called page. So the page table assists in finding out the frame number corresponding to the page number. You can see that 0th page, or the page table is indexed by the page number. So 0th page is stored in frame number 1. and that information is given in the page table 0, 1. The 0th entry in the of the page is 1. First entry number entry of 1 in page number is page table is 4. That means is stored in frame number 4. So like this is actually the concept of paging. Now let us see what is the hardware support, or how this address translation is done. When CPU wanted to access an instruction or data, it will generate the logic, but the instruction or data is stored in memory. So to access that instruction, a physical address should be obtained. So this translation of the address is done by the underlying hardware. So that we're going to talk about the hardware. When CPU generates the address, it is a logical address which is divided into page number and offset. Means there are m bits in the address. N bits are used for offset and m minus n bits are used for page number. Don't worry about the number of bits in the page number. Assume that some bits are used as a page number and some bits are used as offset. This page number P is actually an index to the page table. You can see the page table downside. Page table is indexed with the page number, and by looking into the entry, or the if it is P, the P, looking into the P entry in the page table, we can get an F, which is nothing but the frame number of the frame in which that particular page is stored. That F frame number, actually the frame number gives the number of the frame in which that particular page is stored. And we have offset, another field, the next field of logical address. Offset gives within the page where the instruction could be found. Because CPU generated a logical address for instructional data. Offset gives within the particular page where this instruction or data could be found. Or it is nothing but the relative portion of the instructional data that particular page. Since the size of the page is equal to the size of the frame, the relative portion of the instruction in the page will be same as that of instruction in the. It is just like a line number in the page of a book. If we copy the third page of a book into fifth page of another book of same size, the relative position of the line number doesn't change, provided the font size is same. So like that, the offset in the page will be the same as the frame. By combining F and D, we will get the physical address. So we can compute the physical address using this hardware once if a logical address is generated with the help of the page table. Now let us talk about size of the page. How the size of the page number of bits in the page number of bits in address, number of bits in offset, everything is calculated. As we know, using k bits, we can address 2 raised to k locations uniquely. Hence, in order to address n locations, we need log n to the base 2 bits. Right? For a given specification of system, the RAM size will be given. That is the size of number of bits, number of bytes in the RAM will be given. So we have the number of locations to be addressed. Based on this, we can compute the number of bits required to address the RAM. And say let it be M. Next, we have the size of the frame also will be given in the paging scheme. So we can compute the offset takes a value starting from 0 to the maximum value 2 raised to n if there are n bits. So the size of the frame or the value of offset varies from 0 to size of the frame. Usually, the size of the page is taken as a power of 2 to exploit all the address space generated by these n bits. And also, it helps us to translation of the page number and offset. So here, the figure shows that bits in relative address, m bits are there.
ഹലോ സർ വീഡിയോ ഒന്ന് മ്യൂട്ട് ചെയ്താൽ എനിക്ക് തോന്നുന്നു പാർവതി പറഞ്ഞു അതിൽ കുറച്ച് ബഫറിംഗ് ഉണ്ട്. ആം ഐ റൈറ്റ് പാർവതി? ഹലോ പാർവതി സർ, വീഡിയോ ഒന്ന് ഓഫ് ചെയ്യുകയാണെങ്കിൽ ചിലപ്പോൾ അതൊന്ന് ഓക്കെ ആവും. ശരി, താങ്ക് യു.
Thank you. That is, if there are m bits in the relative logical address or relative address, can be divided into n bits for the offset and m minus n bits for the page number. Now let us take an example how to compute the number of bits required for page number and number of bits required for offset, number of bits required in address field. Assume that there are 32K RAM and we have the size of the frame as 2K. The number of bits in the physical address will be, we have to address 32K locations or 32K bytes or 32K words. It is 32K is equal to 32 into 1024. That is 2 raised to 5 into 2 raised to 10. To address 10 raised to 15 locations, we need 15 bits. So the number of bits in the physical address is 15. The number of bits in offset, as I told you, the offset varies from 0 to the size of the frame. So the number of bits D in offset is equal to the number of bits required to address these 2K size, all the locations in the 2K size frame. So number of bits in the offset is logarithm of 2048 to the base 2, that is equal to 11. Then total number of frames. Total number of frames will be, the total size of the RAM is 32K, size of one frame is 2K. So the total number of frames equal to 32K divided by 2K. So that many number of frames will be there. That is 32K by 2K is equal to 60. The maximum number of entries in the page table. Maximum number of entries in the page table is, suppose that the memory RAM is fully loaded with the pages. So corresponding to every frame in memory, there should be an entry in the page table. So the total number of entries in the page table will be total number of frames in the RAM. So that is 60. The number of bits required to, then the number of bits required in page number, that is number of bits in P, is the number of bits required to address these 16 locations. 16 locations of page table. This page number is an index to the page table. So 16 locations in the page table shall be addressed using 4 bits. So when we have 32K RAM and 2K size frame, the number of bits in the address is 15 bits. Number of bits in offset is 11 to address these 2K locations. Number of frames is equal to 32K by 2K is 60. Maximum number of entries in page table is 16. The total number of frames in the RAM. Number of bits in page number is number of bits required to address these 16 locations of the page table, that is 4. Now let us take an example how this address translation is done. On the right side you can see the main memory, which contains 16 frames. Assume that we have a 32K RAM as in the same example. 32K RAM is divided into 16 frames of 2K size each, and CPU generates an address of length 15 bits. Logical address, number of bits in logical address will be same as the number of bits in the physical address in almost cases. Now imagine that CPU generates a logical address 0011, 0000 and 1001. That is, the page number takes 4 bits, as I already told. When the frame size is 2K and total memory is 232K. The page number is 0011, offset is 0000, 1001. That is third page. 0011 stands for 3, decimal 3, and offset is decimal value of offset is 9. Third page, 9th word. P is an index to the page table. So let us look at the frame number. Look for the frame number corresponding to page number 3. It is 1010. A frame number is taken and is appended along with the D. We will get the physical address. So for the logical address, third page, 9th word, we get 10th frame, 9th location. Clear? This is how this address translation is done. Now, as I told you, this physical address is computed by appending the frame number with the offset. But when the frame number is given, say F, to compute the physical address, actually we have to multiply this F by size of the frame, so that we will get the starting address of the Fth frame. To get the starting address of the Fth frame, we have to travel all the frames from 0 to F minus 1. So the frames have to be, size of the frame has to be added F times. So that's why we do F into size of the frame. And offset when added to that, we'll get the physical address. Now let us look into the other aspects of paging. We have already seen the hardware, what is paging, the hardware support for paging, then how the number of bits in frame, number of bits to address the page memory, number of bits in frame, page number, offset, everything is calculated. And an example we have seen. Now let us look into other aspects. Paging suffers from internal fragmentation. Means when the size of the page is not exactly a multiple of size of the page, because page is divided into, a program is divided into different pages, right? When the size of the program is not exactly the size of exactly the multiple of a size of a page, the last page of the program will contain unused spaces. And in a multi-programming environment, we will have multiple programs, and the number of half-filled pages will be equal to the number of total number of programs in the RAM. So when the total number of programs is large, this wastage is also huge. The space, unused space, remains internal to the page. That's why we call this as internal fragmentation. In order to reduce the internal fragmentation, we reduce the size of the page. Typically, the size of the page is from to 8K. Sorry, 4K to 8K. Another aspect of paging is that it doesn't support users view. User think that our program is stored in the contiguous locations in memory, but paging divides the program into fragments of equal size and kept at different locations. So it doesn't support the user's view. Another aspect is a frame table. So operating system has to keep track of the frames which are free and frames which are used. So this information is the information about the unused frames is kept in a table called frame table. Now let us see the implementation of a page table. How the page table is implemented or how this page number is stored. So far, we have seen that the page table of all processes are organized collectively to form a huge page table. But practically, every program or every process will keep the details about its page table. So in the process control block of a program or a process control block of a process, we have one additional field provided, which is PTBR, page table base register. PTBR stands for page table base register, which stores the address of the location from where the particular process page table is stored. The page table base register is a field in the process control block which stores the details of the page table of that process. This storage of the storage or how this page table is stored plays an important role in deciding the execution time of a program or execution time of a process. Because in order to access an instruction, first the CPU will generate the logical address, and using the logical address, using the page number, we have to refer the page table and get the frame number. After getting the frame number, we'll compute the physical address, and then again we have to access the instruction. So before accessing every instruction, we should conduct a search in the page table to get the frame number. So the response from the page table or the speed of response from the page table plays an important role in deciding the speed of accessing an instruction, which subsequently leads to the execution time of a program. An obvious way of storing the page table is in CPU registers because they are the fastest and will get the response very fast. But the problem is when the size of the page table is very large, the CPU registers will be insufficient to hold this huge page table, or the number of registers will be insufficient to hold this huge page table. Say for example, if we have a RAM of 4 GB and a frame size is say 4K, then 2:20 entries will be there in the page table. So this number of registers are very, very few compared to the 2:20 locations required for storing the page table. So obviously we'll go for the main memory to store the page table. Main memory is used, we will have enough space to store the page table, but the problem is, in fact, we need two memory access to get to access one instruction or to fetch an instruction. To fetch an instruction, the CPU will first generate the address of the instruction, which is the logical address, and from there you will take the page and access the page which is in memory, then get the frame number, form the physical address, then again use that physical address access the memory once again to get the instruction. So the fetch of an instruction takes 2 memory access, which will reduce the speed by 2, speed of execution by 2. So that's why nowadays we use a separate storage mechanism, which is called a translation look aside buffer (TLB) for storing the page table. TLB is associative memory. It is high speed memory, but a costly memory. So we have only limited amount of associative memory to implement TLB. The clarity of associative memory is that every entry in associative memory consists of 2 parts. That is a tag and a value. Every entry has 2 parts, tag and value. When it is basically this associative memory is used for lookup operation. That is for searching operation. When an input is presented to the associative memory, it will compare the input with all the tags in parallel, not in sequential. It is compared in parallel. And if a match is found, the corresponding value will be given as the output. That is the working of associative memory. So this makes the parallel search makes the memory suitable for search operation. So this shows how the page table is or TLB used for storing the page table. You can see that the CPU generates logical address, and it is divided into page number and offset, and page number is checked for page on cache. Page on cache decides to determine or it sees whether the particular page number is available in the TLB or not. See, we have limited amount of TLB, so we have limited amount of associative memory. So TLB contains only some of the page table entries. The logical address given to page number and offset, and P is presented to TLB, and corresponding to first the page number is checked in the TLB. If frame number is available, if the entry is available in the TLB, corresponding frame number is obtained from the TLB. Otherwise, we'll check. So anyway, this entire page table will be there in the main memory. So if it is not available in the, it is not obtained from the TLB, we will search the main memory or page table kept in the main memory to get the F, and appending it with the D, the offset will compute the physical address. If the particular frame number is obtained from TLB, it is called a TLB hit. Otherwise, it is a TLB miss, just as a cache hit and cache miss. In case of TLB, we define a measure called hit ratio. The hit ratio is the ratio of total number of, the hit ratio is defined as the ratio of number of hits to the total number of requests sent. Our objective is to increase the hit ratio with the minimum amount of TLB. Once if we use TLB, we have limited amount of TLB. our objective is to increase the hit ratio, get a maximum responses from the TLV itself for the frame number. For that, we use some sort of locality of reference. So nowadays we use TLV for storing the page table. Now let us discuss the advantages of paging. One of the key advantages of paging is that one of the key advantages of using paging for memory management scheme is that we can share the common code, or the possibility of sharing the common code. When multiple programs or multiple processes share the common code, it is enough to keep the code exactly once in the RAM. Exactly one copy is needed to be kept in the RAM only. In the logical address space of the program or the process, each process will feel that it has its own copy in the RAM. Or in the logical address space, they keeps these pages as their own. Look into the figure. Memory is divided into there are 11 frames and processes P1, P2 and P3. A editor program is used by all the processes. ED1, ED2, ED3 and data are the pages of the process. You can see that ED1, the page ED1 is stored in frame number 3. Page ED2 is stored in page number 4, sorry, frame number 4. And page ED3 is stored in frame number 6. Each process will have its own logical address space and they are divided into pages. But we look into the page table, we can see that 0th page of process 1, 0th page of process is mapped onto the page, the frame number 3. ED1 is stored in frame number 3. Page number 1 of process P1 is stored in frame number 4. Similarly, the 0th page of P2 ED1, in the page table it is shown that the 0th page of ED1 is stored in the frame number 3, here in frame number 3. 0th page of P3 also is having its own logical address space but mapped onto the frame number 3. The thing is that it is enough to keep exactly one copy of the program that is shared, so that we can save time, save the space. Now let us see the next advantage of paging, that is protection of pages. Protection, basically the meaning of protection is that prevention of the illegal access. Here, by you, in the concept of paging, we can protect the frames from illegal access. Associated with or in the page table, associated with every page, there will be a bit, valid, invalid bit. If the bit is valid, then the access to that particular page is permitted. If it is invalid, the access to that particular page or the frame of corresponding to that page is not access is not permitted. So using a valid invalid bit along with the page table, we can prevent the illegal access to these frames. In the figure, you can see that 0th frame, 0th page is stored in frame number A. That is 4th frame or frame number 4, and the frame number is written in the page table. 0th page, frame number 4. It is valid, hence it is permitted to access frame number 4. And page number 1 is invalid. So wherever it is stored, it is not permitted to access. So this is another advantage. The protection is possible if you use paging for memory management. Next topic is multilevel paging. When the size of the page table, see, page table is kept in main memory. Main memory is divided into frames. If the size of the page table is more than that of a page, anyway, when we keep in main memory, this page table is to be kept in main memory. So when the size of the page table is more than that of a page, the page table itself need to be paged. Consider we have an 8 GB RAM with the frame size as 2K. Then it needs 8 GB is 2:3 into 2:30, so 2:33. The number of entries is 2:33 in the main memory. So it is divided into 2:22 frames. When we divided 2:33 by 2:11, that is size of the frame, we get 2:20. So the total number of frames will be 2:22 in the RAM. Correspondingly, we will have 2:22 entries, or we have maximum 2:22 entries in the page table. But we know that size of a frame or a page is only 2:11, that is 2K. In order to store these 2:22 entries, we have to again use 2:11 frames in memory, because the page table need to have 2:22 entries. In order to store these 2:22 entries, one page will not be sufficient, because maximum one page can hold 2:11 entries. So 2:22 by 2:11 will give again 2:11 pages or the frames are required to store this page table. So that forms the first level. Here you can see that 2:22 entries we need in the page table. So definitely 2:11 pages will be there in the page table. In order to address these 2:, or in order to keep the frame number of these 2:11 pages, we should have another page table, which is the outer page table. So this outer page table will keep the frame number, in which frame number of each of these each of the pages of the page table, and these page table will contain the frame number of the particular instruction of the main memory. When CPU generates an address, it is divided into 3 logical address. When a CPU generates a logical address, it is divided into 3. P1, P2, and D. So P1 is a pointer, or P1 is an index to the first outer page table. The outer page table will give the frame number of the frame in which the frame number of the intended, or frame number of the frame which contains the intended instruction or data. And CPU generates a logical address for accessing instruction or data. It is divided into three. P1 points to P1 is an index to the first level outer page table. This will give the frame number of the frame in which the frame number of the main memory in which the intended instruction contains is stored. So after taking this F1, we'll go to the frame. This is nothing but the one of the frame of the page table, and this actually, in this example, this particular frame will contain 2^11 page table entries. After reaching this particular frame, we need to find within the frame which entry in the page table we refer. That is given by P2. That is, index in the inner page table is given by P2. If we travel P2 distance from the starting address of this particular frame, we will get the frame number of the frame in main memory where the intended instruction is stored. After getting the F2 from the inner page table, we can add the offset D, or if we travel D distance from beginning locations of the location of the frame F2, we will find the actual instruction. So this is a multi-level paging. So multi-level paging is used when the size of the page table is more than that of a page. We have to page the page table. That is how the multi-level paging comes. So with this, I conclude the talk on non-contiguous memory allocation.
Thank you, sir. We have some questions. Can we discuss that?
Yeah, sure.
Okay, sir. The first question is, could you please explain the example for address translation once more? Could you please explain the example for address translation once more?
Yeah. Can you see the slide? Can you see my desktop now? Hello?
Yes, sir.
Yeah.
Yes, sir. We can see the desktop.
Yeah.
Now it's multi-level paging screen.
Yeah. Now it is multi-level. This is address translation, is it not?
So it's now
Hello?
it's here visible as that multi-level paging is visible.
Okay, it may take time, I think. Now can you see the address translation example? Hello?
Hello, sir.
Parvati?
Hello, sir.
Now the desktop shows.
The same page itself, sir.
Hello?
Hello.
It is not address translation.
No, sir.
Hello?
Hello, sir.
Yeah,
It is showing the same page
I'm
itself.
trying to get this. Is it address translation? No,
No, sir.
it's multi-level paging.
Yes, sir. Multi-level paging. Hello, sir. We have another question. Shall I ask?
Yeah.
Okay. How
Yes.
internal fragmentation differ from external?
Right. See, interpretation I already explained. I think it is understood. It is as usage of space internal to the page. Not about the contiguous allocation. The need for non-contiguous allocation. I hope you remember that. So after some process or complete execution, they terminate and the calls are created in the RAM. Suppose that we have calls random places. Say 2K, first hall is 2K, then other hall size 3K, and after another is have 4K like that. So in total, size 2K, 3K, and 4K. So unused space is 2K. When a new process of 9K comes, when a new process requests space in memory for 9K, we cannot allocate it because in they are not continuous consecutive locations are not have to cut these holes into single unit. So scenario that we have space in, unused space in memory. We cannot allocate this space to the program just because just not contiguous. That is the external fragmentation. So it's not internal to any page or any segment. The external fragmentation is not internal to any page or internal to any block. It is outside that block. But in non-contiguous allocation is free from fragmentation, but it suffers from internal fragmentation. Clear?
Hello, sir.
Hello.
Hello, sir.
Yeah. Can you see the slide? Address translation slide now?
No, sir. We cannot see. Sir, no issues.
Any other question?
We have some few more questions, but we have reached 1 hour. So we will share the questions to you separately and we'll collect the answers. Hello, sir. Sir, we have a time constraint. So we will share the questions asked by students to you separately and we'll collect the answers. Hello.
Yeah.
Hello.
Yeah. Can you
So,
see the slide now? One
sir, now
question they
we can
asked.
see
No?
yes, sir. Now we can see this slide. Sir, could you
Sir, explain that address translation. You have time? Hello.
hello?
Yeah.
Sir, could you please
This
make it
is
fast
the
because we
slide
have
for
reached time limit.
yeah.
Sir, we can see the slide.
Yeah, that's right. Slide you can see. No? Yes.
Yes.
So here it is an address translation example. The same problem that you have done in the previous slide. Say 32K size RAM and frame of size 2K. So here we have 16 frames in memory. The CPU generates a 15-bit address because in order to address these memory locations we need 15 bits. So the logical address contains 15 bits, which is divided into page number and offset. As I told you, page number contains 4 bits as there are 16 entries in the page table, and offset contains 11 bits. This page number is pointer to the index to the page table. So 0011 it's 3. So 0011 the page the 0011th entry, that is the entry in the third position, is 1010. This is the frame number. This is the frame number corresponding to 0011. So once we get the frame number, it is 10. 1010. The decimal value is 10. So we will go to the 10th frame. You can see here the frame numbers given 0, 1, 2, etc. 10. So we will go to the 10th frame, and in the 10th frame we will look for the 9th entry. So this is 9. The relative position of the instruction in the page is same as the relative position of the instruction in the frame. So the third page is stored in 10th frame. That is written here. That is recorded here. The page table 0011 corresponds to 1010 frame number. This frame number 1010 followed by 00000 etc. 1001 will give the physical address. That's how this translation is done. First, logical address is divided into page number and offset. By using the page number, we'll find out the frame number. Frame number, when appended with the offset, offset remains the same. So when appended to the offset, it will give the physical address. I hope this is clear now.
Okay,
Hello.
sir. Sir. Hello, sir. I hope the students got
Yeah.
the doubt cleared. So now we are
Yeah.
winding up the session due to time constraint.
Okay.
Praveen sir has given a wonderful session here. He took a great effort in preparing the session and making it so easy to understand. Thank you so much for your time and patience, sir, for taking this session.